overlay that can be denoted by wood notation. They are simply related. So here we have a discussion of this matrix algebra will satisfy this case A structure that we got. Okay, so here I write the wood notation. You have P 1 by 1, primitive 1 by 1, or center 2 by 2. Right? Sometimes center 2 by 2 is also written as root 2 by root 2 R45, right? Because it's rotated by 45, and that is the length of the overlay structure rotated by 45 degrees. And that corresponds to this matrix notation, the transformation matrix go from one substrate to the overlay. And then you have P2 by 2, that's a common one. C2 by 2, P2 by 2 are common, quite common for metals, overlay structures, so nickel, moly, copper, things like this. For the 100 surface, they often have C2 by 2 or P2 by 2. You're talking about absorbing on these single crystal surfaces. And then you have you can see the wood notation is always sort of 2 by 2 or 1 by 1, primitive or center, this sort of thing. And they are all integer related in the matrix notation. So they are equivalent in this type of writing. And then you have a situation where you cannot use the wood notation anymore. They are not simply related. They are called rationally related. So if the determinant is a rational fraction. So again, I remind you, what is a rational number? A rational number is just a fraction consists of two integers, right? So it could be 1 divided by 2 or 3 divided by 2, this sort of thing. So these are rational fractions, okay? And the determinant is the integer, right? So the area ratio is a nice integral, so it's multiple. The substrate, the overlay area is a multiple of integer multiple of the substrate area. So that's what this integer means. And some of the matrix elements are not integer; they are fraction. They are rational fraction. Yes, they could be fraction. Then in this case, they are rationally related. It means that the two mesh will come in sync in regular intervals. So you can think of this, you have the blue is my substrate, the red is my overlay. So every 3 atoms, right, they may come in sync with a blue atom. So that's what we meant by rational related. They coincide every other one. The absorbers are incommensurate, so-called incommensurate respect to this. And then finally, you have case 3, which is rather complicated situation when you have very interesting reconstruction. This determinant is no longer rational fraction. They don't relate it to multiple fraction. The two areas are not related to multiple fraction. Rather, they are related by a irrational number. For example, square root 2 is a irrational number, or 1 over square root 2 is also a irrational number. Things like this. Okay, so that's what it meant by irrational. That means that there's no periodicity between the two mesh. They have incoherent structure, so that would be the ice on metal case, right? Ice on nickel case. That would be a incoherent structure. Ice will form its own thing, and nickel form its own thing. There's no relation between the two layers that we have. Okay, the surface is termed incoherent structure, and really what it does is that the substrate just provides a flat surface. So that the overlay, the absorbent, can form its own thing. So water can form ice in its own hexagonal structure at the right temperature, or cubic structure you go lower in temperature. Okay, so the absorbent overlay are also incommensurate, and they have incoherent structure, whereas the case B will be coherent structure but incommensurate. Okay, so incoherent structure, for instance. And they usually occur when the absorbent interaction is so strong that the absorbent don't really want to form bond with the substrate. it just like to form bond with the cell. It's kind of an antisocial absorbate. It doesn't like to interact with the substrate to make good connection. So water is a very good example of what you see. Okay, so here I just, in green, I just talk about the confusing word about substrate that we just discussed at the beginning of the lecture. When we use the word substrate, it could mean different things when we are talking about either clean surface or absorbing cover surface. Okay, I don't want to go into, we just discuss this. And then finally, we talk about something called step services, and this is a big deal. That make this guy by the name of Gabor Samajai, a very famous professor at Berkeley, UC Berkeley, make his name in the 70s. Is that Gabor Samajai is a catalyst, so he studied catalysis, and what made him famous is that he was the first, if you like, the first service scientist trying to understand catalysis by studying step services. So his hypothesis is like this. His hypothesis is that, well, the catalysis is usually a complicated particle, nanoparticle usually, right? So a classic example would be these copper oxide or nickel oxide nanoparticle that is studied in chemical engineering, and chemical engineers use this metal oxide a lot in their reforming reaction, right? The so-called organic reforming reaction to make petroleum, for example. So you go to ChemEng here, they have a real reactors, 3-story high reactor that sort of stimulate, they test catalysis that way. So what Gabor said is this, is that, well, this nanoparticle is a very complicated structure, but we know one thing, we know that the reaction occur on the surface, okay? So if we can, and so far all the chemists have been studying low Mueller indexes like 100 and so forth. It really does not represent what's really on this complicated particle, because this complicated particle probably have many different phases. And in particular, they have something called step services, which are not low Mueller index services. So Samajai started, and his group at Berkeley started systematically, very systematically in fact, study multiple of these step services, and they require a very good crystallographer to make all these services. And okay, so to make, you guys hear me? I can see a feedback here coming through. Okay, so. Okay, so you can still, the glow side, can you still hear me? Sorry? Oh, I can't hear you though. If you can hear me, move your hand. Okay, thank you. Okay. So Samajai trying to study this step services rather systematically, and his major thesis was that these step services are very reactive. So if I can understand the reactivity of these highly reactive surfaces, then I can get a handle on understanding catalysis. So that was basically the premise. And he had written 2 books, and the 1972 book will really summarize a lot of his data of step services. And subsequently, he wrote a second book, I think 10 years later, and he again summarized, updated his book. Okay. So what is a step services? A step services is a high Mueller index surface, and the way you think about this is you can think of a high Mueller surfaces into 2 types, into terrace and ledge, right? So basically, so you can reclassify step surfaces, break it down into a notation like this. So your high Mueller index surfaces can be a multiple atom on the terrace face, right? This is the mirror surface of the terrace face, and this is the mirror